Imagine boarding a $300 million Boeing 777 for a flight to London, and the moment you step off the tarmac, the airline simply pushes the plane into the ocean. To fly back, they have to build a brand new jet from scratch. For over 60 years, this was how we accessed space. We built towering, multi-million-dollar rockets, launched them once, and let gravity drop them into the sea. The industry is now moving toward VTVL, vertical takeoff, vertical landing. The objective is to operate orbital rockets like commercial airliners: launch, land, refuel, and launch again. Launching a rocket is one thing, catching it is another. Bolting landing legs to an old booster doesn't make it reusable. The engine itself has to survive a return flight it wasn't originally built for. To withstand multiple trips, an engine's internal anatomy requires a complete redesign to handle 3 specific physical hurdles. It cannot melt, it cannot clog itself with carbon, and it must possess the precision to hover. Inside a rocket's combustion chamber, temperatures regularly exceed 3,300 degrees Celsius. Without protection, the standard aerospace metals used to build the engine would simply liquefy. Engineers can't just use thicker metal walls to stop the heat. Every extra kilogram of copper or steel added to the engine is a kilogram of cargo that never makes it to orbit. The solution is a system called regenerative cooling. This diagram shows the process. Instead of letting the walls absorb the heat, sub-zero cryogenic fuel is pumped through thin internal channels. The fuel pulls the heat away from the metal before it enters the chamber to be burned. Manufacturing these channels requires extreme precision. This laser-welded sandwich structure creates thousands of individual cooling paths separated by millimeter-thick walls. They must hold back the high-pressure fluid without bursting or melting into the 3,000-degree inferno. Regenerative cooling turns the rocket's own fuel into a protective heat shield. It prevents a meltdown while preheating the propellants, making the combustion more efficient. Surviving the heat is the first step, but a reusable engine can't afford to clog its internal plumbing with debris during a flight. Standard rocket kerosene, or RP1, undergoes a process called coking when it gets too hot. Above 480 degrees Celsius, the fuel decomposes, leaving sticky black carbon deposits throughout the engine's valves and cooling channels. This carbon buildup creates a maintenance nightmare. After every flight, the engine has to be taken apart and scrubbed with chemicals to clear the pipes before it can safely fly again. To solve the coping problem, engineers are moving to a different fuel, liquid methane. Methane is a much simpler molecule than kerosene. As this diagram shows, it burns completely into carbon dioxide and water vapor, leaving the internal surfaces of the engine virtually spotless. Methane also offers a logistical advantage for missions to Mars. Using the Sabatier reaction, astronauts can manufacture methane fuel on site, using Martian ice and the carbon dioxide in the atmosphere. By switching to methane, we eliminate the need for deep cleaning between flights. It turns the rocket into a vehicle refueled and launched in hours, not weeks. The final challenge is landing. A returning rocket is nearly empty and incredibly light, but rocket engines are designed to fire at 100% power to fight gravity. Firing a standard engine at full power would just shoot the empty rocket back into space. To land vertically, the engine needs to act like a dimmer switch, dropping its thrust low enough to achieve a gentle hover. But turning an engine down is dangerous. Low flow rates can lead to chug, a violent combustion instability, or cause the liquid oxygen to boil. These oscillations can shake an engine apart in seconds. Engineers overcome this through a process called deep throttling. This requires sophisticated variable valves acting as brakes on the turbopumps. They restrict the total fuel volume while ensuring the pressure drop at the injector stays high. Maintaining high pressure keeps the fuel perfectly atomized and combustion stable, even when barely running. This level of fluid control allows an engine to drop from 100% thrust down to as low as 17% without flickering out. Perfecting deep throttling gives a machine built to produce millions of pounds of force the finesse to set down a 20-story building safely. To make spaceflight sustainable, we need engines that act as their own refrigerators, burn self-cleaning fuel, and utilize precision valves to hover. We are seeing these 3 systems come together in hardware like the Starship vehicle. Reusability is often discussed as a way to save money on steel and aluminum, but the true shift is in the flight timeline. Without regenerative cooling, methane combustion, and deep throttling, access to orbit remains restricted by the time and cost of building new hardware for every mission. Perfecting these systems turns the rocket from a single-use laboratory into a standard transport vehicle. Keep experimenting.